Qualcomm Technologies, we are at the forefront of developing 5G non-terrestrial network, or NTN technology, to make ubiquitous broadband a global reality for billions of users. Our cabled 5G NTN testbed is calibrated for multiple elevation angles and slant ranges of LEO satellites. It allows us to rapidly test NTN features on our modern RF platforms. With the testbed automation, we validate the platform robustness for an extensive set of conditions. Long delay, high Doppler shift, and high path loss of LEO satellite channels are emulated by a channel emulator. Since the mobile test platform, or MTP's antenna system, is not included in the cabled testbed, the channel emulator also models the antenna effects such as gain, diversity, and polarization. With our over-the-air, or OTA testbed, which is calibrated for the power flux density, or PFD, measured independently of the MTP, we improve the fidelity of our NTN test platform by including the MTP antenna system. While a channel emulator is used to create the LEO satellite channel, the OTA testbed provides a realistic view of MTP performance without any assumptions on the MTP antenna system. This 5G NR-NTN scenario shows an emulated LEO satellite 600 kilometers above the ground and a user equipment, or UE, provisioned at a location off the coast of Baja California. The radio head moving on the circular track emulates the motion of the LEO satellite. A channel emulator is connected to the radio head to introduce the delay, Doppler, and path loss for the satellite channel. The satellite serves the UE starting from the minimum elevation angle of 25 degrees. The slant range varies from 600 to 1200 kilometers, and the Doppler varies from -44 to 44 kilohertz during the satellite's coverage, which lasts for about 5 minutes. Our GUI visualizes the test scenario and shows live performance indicators such as signal-to-noise ratio, throughput, delay, Doppler shift, and more. We see that a video call on the device is carried by an NTN connection through the satellite, successfully demonstrating the connectivity at a remote location without terrestrial network coverage and setting the foundation for more complex test scenarios. Let us now return to our cabled testbed and look at how devices can benefit from non-terrestrial networks to complement terrestrial networks for robust and ubiquitous services. Here we have a scenario where the device is in the terrestrial network coverage. When a local disaster disrupts the terrestrial network services, the device loses connectivity to the terrestrial network. The device then switches to the non-terrestrial network for service continuity. While being connected to the non-terrestrial network, the device hands over between satellites as they move in orbit. Finally, the device switches back to the terrestrial network when the terrestrial network is restored. The video call of the device is never dropped, which demonstrates the robustness of ubiquitous connectivity with 5G NR-NTN technology.